Hi, everybody. Welcome back. So today we're going to be finishing up our discussion about universality. So the idea of universality, just to recall, is that on a quantum computer, we say that a quantum a set of gates is a universal if for all unitary inside C 2 to the n by 2 to the n, we end up having that there exists a set of gates G1 through Gn such that, oh, and for all epsilon greater than 0, such that the norm of G1 through Gn minus u is less than or equal to epsilon. Okay, and so this is analogous to universality for a Turing machine, where for a Turing machine, we demand that every function on the input bits can be computed using a sequence of gate operations that we have. So this is, or at least I should say, every function that can be expressed through a truth table can be computed in this sense. So, okay, fantastic. This is how we're going to define universality. The question is, what's our gate set? Well, our gate set, like our set of gates over here, is fundamentally going to be taken for this proof to be Hadamard T and the controlled NOT gate. Now, we're not actually going to be really using this a gate set directly. Instead, we're mostly going to be taking a look at the gate set H R Z of theta C naught. Now, we can do that because the rotation gate RZ has a lot more properties than the T gate has. So it'll be easier for us to reason about algorithms through the RZ gate, but recognize the fact that H and T can be used in order to be able to construct or closely approximate an RZ gate using the arguments that we gave for single qubit universality. Okay, so those are our fundamental operations. The first step that we're going to need to be able to do this is we're going to need to prove, one, that Toffoli can be made. Okay, well, there's a straightforward circuit that you can look up in Nielsen and Schwang for describing the Toffoli gate. And that circuit is something that we could just use and take that as its proof and validate that it works. But there's enough, I think, intuition behind how we can go about thinking about doing these constructions that I want to guide you through how the construction of building the Toffoli gate or reasoning about the Toffoli gate can be done. So in order to do this, we're basically going to do a couple of steps. First step is the Toffoli gate, recall, is a controlled X gate. Now this, using the Hadamard gate, can be written as a controlled Z gate and Hadamards on either side. Okay, great. So now what we have is we have this particular transformation. And so we're going to want to do the following. So we're going to want to be able to build now a controlled Z gate, because you can see that if we can build a controlled Z gate, then we just have to do a Hadamard transformation in order to be able to transform back. Now, the next thing that we're going to do along the way is we're going to use the fact that RZ of theta is equal to cosine theta over 2 identity minus I sine theta over 2 Z. This, again, follows from the definition that RZ of theta is equal to e to the negative I z theta over 2. Then when you Taylor expand this guy and use the property that z squared is equal to identity, we end up finding, after collecting the terms, the expression on the left, as we've seen many times so far. So if we do this, then note that RZ of pi is actually equal to cosine pi by 2 identity minus I sine pi by 2 z, which is equal to minus I z. So up to an overall constant phase, which doesn't affect anything, the RZ of pi is actually equal to the z gate. So we can build a z gate using an RZ operation. Awesome. So now our trick is to be able to use this and the properties of our z operations. So there's a couple of properties that we're going to want to use. Property 1, x RZ of theta x is equal to RZ of minus theta. The proof for this is easy. Using the property that RZX is equal to x e to the negative I theta over 2 ZX, which is equal to e to the negative I theta over 2 XZX, which is equal to e to the I theta over 2 Z. And this is equal to, of course, RZ of negative theta. So we can see that putting two NOT gates around an RZ gate will flip its direction. The next property, which is a really nice one, is RZ of theta times RZ of phi is equal to RZ of theta plus phi. Now, the proof of this, there's a couple of ways you can do it. Perhaps the best way of going through it is to actually do a Taylor series expansion, group the terms, and see the result. But instead, in the interest of brevity, I'm going to use another proof that boils down to the Baker-Campbell-Hausdorff formula. So this is e to the negative I z theta over 2, e to the negative I z phi over 2, which is equal to, from the Baker-Campbell-Hausdorff formula, e to the negative I z over 2, theta plus phi, minus the commutator between z and z, theta phi over 4 times 2 factorial, plus so on and so forth. Now, the commutator between a and b is just ab minus ba. So the commutator between any operator and itself is always equal to 0. Therefore, this is 0, and we end up seeing directly that the product of rotations is the rotation of the sum of the angles. So that is intuitively exactly what we expect from a rotation, right? If we carry out a rotation through an angle theta, and then we carry out a rotation through an angle phi, these two rotations add up to an angle of theta plus phi. Okay, cool. So now we have those two properties of rotations. The next thing that we're going to want to do is we're going to want to ask, well, what is our, if we think about our controlled Z operation, let's just take a look at the patterns, right? If we imagine a computational basis state A and B thrown in, and some arbitrary state then down at the bottom, psi, we're going to want to have the following mapping. 0, 0, psi goes to 0, 0, R, Z of 0, psi. Now, this is just a silly way of us writing the identity operation, but bear me out for a moment. Okay, 1, 0, psi. So far, all of these transformations are really boring. The one that actually ends up getting interesting is 1, 1 psi maps us to 1, 1 negative I Z psi. Okay, which is equal to, or sorry, I should say, this maps to our Z of pi times I, because our Z of pi, as we showed, is equal to minus I Z, and so therefore I times this is equal to negative I squared Z, because I squared is -1, this is equal to Z. So you can see that this is sort of the truth table that we would get from doing all of the required transformations. Now, the next thing is using the fact that the S, if we take the S gate, which is 1, 0, 0, I, which we can end up writing as up to a global phase as RZ of, how does it work? RZ of pi by 2, I believe. Then we can actually end up expressing this circuit as the following. Or sorry, we can try to build a template that will carry out this transformation. So what we would like to be able to do is we'd like to be able to, carry out a sequence of transformations such that when the two input bits are 0, it'll generate a rotation that has an angle 0, and so on and so forth. But if the two input bits are 1, we want to generate a rotation through an angle of pi, and also at the same time correct this phase that we end up getting in the result. So how can we do that? Well, the easiest way to do this is to note that using the identity that x r z x is equal to r z of minus theta, we can end up seeing that if this is A and this is psi at the bottom, that this output state will be A r z of -1 to the A theta psi, meaning that the direction of the A rotation will, of the theta rotation will flip if A is equal to 1, if we do that. So we can use this in order to monkey with rotation angles and get them to flip up in an appropriate way. And the game is going to be to choose a series of 4 rotation angles such that we can satisfy the rotation angles demanded by all 4 of these equations. So specifically, the way that we're going to do it is by proposing the following circuit. We'll have A and B over here, which again, we're going to assume are just computational basis states. We'll have an arbitrary rotation through an angle alpha, and we'll find alpha later. Then what we'll do is we'll do a controlled NOT gate down here and do a rotation angle through an arbitrary angle beta. Then we'll do our Z through an angle gamma. And then finally, we will do the following here. Okay, now note I put an S gate in here. The reason why is that I need to worry about this pesky phase of I in front of the RZ gate. And so this S gate will apply I if and only if this bit string over here is, oh, I'm sorry, that is not right. Let's not worry about this for the moment. Okay, so we have these individual rotations coming through, and we would like to be able to first match the pattern. of the following. So if we have A and B coming in and they're both 0, then the operation that we're going to be applying to our state is going to be RZ of alpha plus beta plus gamma plus delta. Because if both inputs are 0, then none of these rotations end up flipping the direction. However, if A is 0 and B is 1, then in that case, we're going to have RZ of alpha minus beta plus gamma minus delta. If we have 1, 0, then we get RZ of alpha plus beta minus gamma minus delta. And if we have 1, 1, then the rotation that we end up applying to the bottom state, psi, is going to be RZ of alpha minus beta minus gamma plus delta. And that should be a delta there. Okay, now from these expressions at the top, we end up getting 4 equations. The equations are alpha plus beta plus gamma plus delta equals 0. Alpha minus beta plus gamma minus delta equals 0. Alpha plus beta minus gamma minus delta equals 0. And just to be different, we have alpha minus beta minus gamma plus delta equals pi. Okay, those are our 4 equations that we have, and we have 4 unknowns. So we'd like to be able to go through and solve this. So our expression is this over here, and let's just go through and solve this this guy by adding together the first 2 equations. What we end up getting is we end up getting that alpha, or 2 alpha plus 2 gamma equals 0. And this implies that alpha is equal to negative gamma. Adding together the second and the third equation, we end up getting that 2 alpha minus 2 delta equals 0. This implies that alpha equals delta. Substituting this into the second equation, what we end up getting is we end up getting that beta minus beta plus gamma equals 0. And this implies that beta equals gamma, which is equal to minus alpha. Okay, so what we now have is we've got an expression for beta, delta, but we don't have one for gamma, or so we don't have, yeah. So once we substitute this in, we end up getting, well, alpha minus beta, which is equal to gamma. So we have minus negative alpha minus negative alpha plus alpha is equal to pi. So putting these together, we find that alpha is equal to pi by 4. So our transformations that we end up pulling off are can now be written as using the fact that up to an irrelevant global phase, our z of pi by 4 is equal to the t-gate. This shows that we can implement this as t c naught t dagger t dagger, and then the last one, which is given by C naught, C naught. And now the going through analysis of the angles, we can actually end up seeing that this factor of I that I was a little bit worried about earlier is actually just an overall phase that we end up getting on the bottom qubit. And so this overall constant phase of I that we end up getting with this circuit, because it always ends up firing for this transformation, is not a problem whatsoever. So this is our gate for the control Z. The only thing that we need to do is to turn it into a Toffoli gate is use the Hadamard transformation that we see on slide 1 to fix this. So we need to Hadamard conjugate. And this now is our resulting circuit. Wonderful. So we have shown 1. Toffoli can be built. And the lesson from this construction of the Toffoli gate was that if we're taking a look at building a particular gate, one of the things, a strategy that I find often works really well is to turn that gate into a diagonal gate, as in one that just involves a bunch of phases being applied to input states. I then reduce that to a system of equations that could be solved in order to be able to figure out how to apply different rotations in order to build that pattern of phases. And the rest is, well, pretty straightforward. So that is the strategy that we use to build the Toffoli gate. The next thing that we need to do is show two level rotations can be built. So the idea of doing a 2-level rotation is that we already knew that we could do a single qubit rotation. So we could end up doing something like identity tensor RZ, which basically would end up being something like, if we ended up expressing this, we would have e to the negative I theta over 2, 0, 0, e to the negative I theta over 2. I think actually I did this backwards. This would be e to the negative I theta over 2, e to the I, 0, e to the I theta over 2, e to the negative I theta over 2, e to the I theta over 2. Okay, so we can do these types of rotations, or, we can do like identity times Rx, which is, going to be basically the exact same sort of pattern. What we'll have is that this is cosine theta over 2 minus I sine theta over 2 minus I sine theta over 2 cosine theta over 2. And so you see that what we get from this is we get these kinds of block structures, but there's very specific patterns to how the blocks can end up being formed. Our aim is to be able to actually kind of construct a general 2x2 rotation. So what we would like to be able to do is do a transformation that looks like 1 going all the way down to a row that will do something like 0, A, 0, B, C, D. Okay, where this over here, I'm going to assume is going to be column M, and this is row N. So the basic idea is what we want to do is we want to be able to build matrices that only rotate in the space span MN. Okay, and will act as identity everywhere else. So how can we express these particular rotations? So the way that I'm going to do it is I'm going to say, we're going to want to build a unitary U that will map the state M to AM plus B N. It'll map N to B complex conjugate e to the I theta N or M minus alpha star e to the I theta N. Now we can see that when we compute the inner product between these two vectors, we end up getting that the result is 0. So this ends up giving us basically everything that we kind of need for this being a valid unitary transformation in the space spanned by M and N. We just need also that L chosen to not be in the span of M and N will map to L. So this is the form of the unitary transformation. Now, the Nielsen and Schwang takes a very particular way of implementing this. The way that they do it is by trying to break the problem up or into individual rotations between adjacent numbers using this notion of a gray code. The intuition that I'm going to be using in this proof, and you can use a Nielsen and Schwang proof if you like that better, but the intuition that I'm going to be using is that this over here is actually just going to be a two-dimensional rotation or a two-dimensional unitary. And so we want to, instead, what we're going to want to do is we're going to want to map M and N, or I guess we're going to want to do AM plus BN for some arbitrary A and B. And we're going to want to map this tensor 0 to a state that's of the form junk over here time tensor with A0 plus B1. Now, if we have a state in this form, right, where we've kind of moved our quantum information, instead of being on the junk register out in front like it is here, we've now moved everything to be all the quantum information to be equivalently on this single qubit that we have off to the side. Then if we want to be able to carry out a unitary transformation on just that qubit, then all we need to do is apply U A0 plus B1. Okay, so that's the intuition behind this. And in order to do this, we're going to need a number of different operations. So the very first operation that we're going to define in order to be able to achieve this goal is I'm going to define an operation called add n. And so add n, what it will do is it will end up taking a register M and map that to M exclusive or N. The cost of doing this is going to be order N X gates. And here we're going to assume that M and N are known classically. So there's just some numbers that you know. You've chosen what M and N you want to do before you try to synthesize this. So we know what they are. And worst case scenario, we are going to need, in order to be able to exclusive OR the two together, we're going to need order N X gates to do that, which can be done using order N RZ and Hadamard gates. Okay, so that's the first operation that that we're going to need. The next operation that we're going to need for this is we're going to need a operation I'm going to call controlled add n. And what this controlled add n it will do is it'll map 0 tensor x to it'll map that to 0 x exclusive or I guess I'll call it add m plus n exclusive or m plus n. And it'll map it'll map y not equal to 0 x to y x. So basically what this will do is if and only if the first register of qubits, where this I'm going to assume here is n bits, if this first register is the all 0 state, then it'll end up mapping that to the following. And the number of, we can do this, but and the number of Toffoli gates that we're going to need in order to implement this, if n is the size of this register, forgive the overuse, this is order n gates as well. And, you know, to do this, this is why we needed our construction of the Toffoli gate, because the Toffoli gate is needed in order to be able to control all of the NOT gates that we're moving down. Okay, cool. So we have add n and controlled add n. The next thing I'm going to need is I'm going to need the controlled swap gate. And the controlled swap gate, what it will do is it'll just map 1 psi phi, just like we had in a Hadamard test, to 1 phi psi. And its implementation, in case you recall, can be is the following. So it can be done with order 1 operations. Is in a constant number of operations. So those are our primitives. Now let's take a look at how we will solve this particular problem. So coming in, we've got a state that I'm going to assume to begin with is of the form AM plus BN. I really should have just called them X or MY. I apologize. Tensored with a bunch of extra qubits, 0. I'm not going to keep track of how many we need for the moment, but if you want, we can envision that there's like L of them. So very first thing we're going to do is we're going to take this circuit, and then we are going to put this into the I'm going to put this into the add n operation. Now, what this will do, coming out the other side, is this, or actually, I've already screwed up the diagram for this. Okay, so we have, to begin with, we're going to have a state that is going to be of the form A M plus B N over here. I'm going to assume for the moment that I've got 0. This is a length n. down here. And I'm going to assume that I've got one extra quantum bit down here. So the first step that I'm going to do is I'm going to apply add n to this. Now, this state over here at this stage is going to be of the form. Now, a m exclusive or n, let's make it add m, a exclusive or m plus b n exclusive or m. Okay. Now, what I'm going to want to do is I'm going to want to apply a controlled add n plus m over here. And so if we do this, then the state that we end up coming out with on the other side is going to be a 0 n plus m, or b n plus m 0. Okay, so this is our quantum state that we have at that stage. Now, what we're going to do is once we have this, I'm going to just do a sequence of a n-fold controlled Toffoli gate. So specifically here, this is using a sequence of n Toffoli gates to flip this quantum bit, the bottom quantum bit, if and only if all of the bits on top are 0. So specifically, right, if we were to like draw this all out, this would end up looking like 0 going down to 0 and then C naughting the bottom. So this can, from the first homework assignment, this can be implemented using order n Toffoli gates, where we call the empty circles mean that the gate is applied if and only if the input is a qubit is 0, not 1. So we can end up doing this process using n different Toffoli gates. Now, the next step that we want to do is we want to do a controlled swap here. Okay, and again, the way that the controlled swap operation is being done is the controlled swap operation has a single qubit, right? And it's got a bunch of different registers. So the way that we're actually doing it is we're doing a controlled swap here. Between the bottom qubits, say, of both registers, and then continuing this process, doing a controlled swap between the last two registers. Everything considered, we need order n C swaps to carry this out. And so because we need order n controlled swaps, this process ends up requiring order n gates. Okay, cool. And so now let's just take a look at what these transformations have. Before doing the Toffoli gates, we ended up having a state that's of the form, like at this stage over here, we had A0, n exclusive or m, plus b n exclusive or m 0. and this is 0 down here. Now the controlled nods going down are going to give us a 0 and exclusive OR M 1 plus B. Oh, and this should be a 0 over here. N exclusive OR M 0 0. Okay. Well, for convenience, let's actually do let's apply a X gate here. Okay. Now applying the X gate is going to flip the bottom qubit to 0 plus B and exclusive OR M 0 1. All right. Now the controlled swap operations, they're going to perform, if the bottom qubit is 1, a swap between these two registers here. So swapping those two will give us a 0 and exclusive OR M 0 plus B and exclusive OR M, oh, sorry, too much copying. 0 and exclusive OR M and 1. Now, something kind of magic happens here, right? What we've got is we've got this tensor factor that's common to both of the terms. So using the distributive property of tensor products, we can factor this as 0 tensor n exclusive OR M. A 0 plus B 1. Okay. And so now that we've written it in this, this particular form, what we can do is we can note that this is actually exactly of the form 0, or exactly of the form junk tensor our state A0 plus B1. So we've done this kind of active transduction of moving the quantum state inside this like a logical two-dimensional block inside a big matrix. We've moved our quantum state from here into an ancilla qubit. And this ancilla qubit can now be modified to our heart's content. So if we wanted to apply a unitary transformation to it, we could apply a U here. Now, looking at the total number of gate operations, we argued this is order n gates. This is order n gates. This is order n. So the total number of operations needed in order to be able to carry this out is order n. Now, there's one itsy bitsy little problem with this circuit. The circuit, if we wanted to apply a unitary transformation down at the bottom, the problem is that we want, this circuit will do the correct transformation to the NM space, but it's not guaranteed to do the correct transformation to other vectors. So for example, if we have L not in span and M, then we need to have our transformation act trivially on it. So if we have, let's imagine now we have the exact same circuit, right? And now I'm going to assume that I have a different state, L, that I put down this. If I start with L, which is guaranteed to not be in the span, then I'll have L exclusive OR M coming through this. And now this is not going to be equal to 0 by definition, because L can't be in the span, and therefore L cannot be equal to M. So this first register is not going to apply anything down here. So this is going to remain 0. And so now what we can do is we can actually take a look at this result and infer whether or not this value is going to be 0. So we want this to be controlled add n m down here. So we want to be able to tell whether or not L exclusive or M is equal to 0 or n. Now, in this case, the only problem that can come up, it can't ever possibly be 0, but L exclusive or M could be n. And so what we would like to do is we'd like to be able to build a circuit that will flip a flag qubit, an extra flag qubit that we're going to keep down at the bottom. And we're going to want to flip that to 1 if and only if L is, or I guess, yeah, we're going to want to flip this to 1 if and only if the top qubit is equal to 0 or it's equal to M exclusive or n. So the easiest one to do is let's do the 0. Okay, so this operation ends up involving n Toffoli gates. Okay, and now what we're going to do is I'm going to do a gate that I'm going to define as, like a controlled add, or I guess I should say, we're going to do a flip down here if this is 1, and I'm going to rewrite this control up here. So what I mean by this control box is I mean if this is equal to n exclusive or m, then do this transformation. Now we can build that transformation. Let me just write this all out in more longhand. What we can do is we can add n plus m here. And now if this result is 0, then we'll flip the bottom qubit and we will now unadd n plus m at the top. And this has now the benefit of us determining the value. Now, what we need to do is we need to copy our quantum information down just like we had before. So we are going to take the value of, let's say, this being 0, and copy that in place. Then what we're going to do is we've effectively got our quantum state, and we now just need to do a controlled swap in order to be able to implement this transformation. And now that we have implemented that transformation, all we need to be able to do is just clean up. Or sorry, we need to apply now a controlled unitary to that target subspace. Then what we do is we clean up all of this. And the cleanup operation is just basically the inverse of all of these operations going here. Everything but the controlled unitary. And that is, in essence, our circuit. Now, the only thing that I need to remind you about is the controlled unitary operation. So the controlled unitary that we have in this circuit is an arbitrary unitary transformation. So an arbitrary unitary transformation, recall, can be written as Rz of alpha, Rx of beta, Rz of gamma, which is equal to Rz of alpha Hadamard, Rz of beta Hadamard, Rz of gamma. So therefore, we can express the controlled unitary rotation in the following form. A controlled unitary rotation is of the form okay. So this is a controlled Z rotation. The only catch is that we actually end up needing one additional rotation over here. Our Z of, I don't know, delta. And the reason why is that we can actually technically have a constant phase up here. Now I said that this constant phase delta is like not important at all, but for controlled operations, it actually is, because it will have an observable impact, because some states will see this phase delta and others won't. And so this allows us to put in that overall phase e to the I delta that actually does matter here dynamically because it's being controlled, is in that e to the I delta will appear if and only if this bottom bit is 1. So this is how we can carry out an arbitrary controlled unitary operation. And this, as you can see from the construction down here, requires order 1 gates. This is order n, order n, order n, order n, and so on. Therefore, everything in the cleanup phase is order n. And so 2 level rotations or 2 level unitaries can be require order n operations. So I'm running out of time, but let me just kind of conclude here by giving you an idea about where the last step is going. The last step that we want to do with this is that we have a matrix that's going to be of the form A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, right? And what we want to do is we want to find a unitary that builds it. And the way we're going to do this is, if I call this unitary U, we're going to want to have a set of gate operations that are going to be of the form G1 through Gn, such that when these operations act on U, we actually get the identity. And this ends up implying that if G1 through Gn are unitary matrices, that the adjoint of that sequence of gate operations is equal to U. So this is just an algebraic trick that it makes it easier to solve the problem, because now we're trying to compile into a fixed matrix rather than making sure that all of the individual arbitrary values of A, B, C, and D are valid. And so the way that we do this is that our controlled 2-level unitaries allow us to take a block of this matrix, say that block, and perform a unitary transformation on that block of the matrix. If we're going to choose this unitary transformation so that it implements the transformation of the form, this maps to, let's call it A prime 0, 0, B prime. Okay, so we will begin by applying a 2-level transformation to that space, and it'll mess up B prime. But then what we're going to do is we're going to want to continue this. We're going to want to do a 2-level rotation on this space over here. And by doing this rotation, we can turn this into A double prime, that to 0, that to 0. Or sorry, that won't be 0. This will be K prime and 0. And we'll continue going through all of this, zeroing out one element at a time. And this process is going to allow us to reduce the problem of unitary synthesis to the problem of implementing these two-level rotations, which we've just seen that we can do in time that's linear in a number of bits, not exponential. And so this is going to allow us to, well, construct the entire matrix. So thanks a lot. Next time, we'll cover the rest of this, and we'll go on to query complexity.